in the polar and tropical stratosphere using in situ measurements from a balloon-borne Frostpoint hygrometer and involved overwintering at McMurdo Research Station in Antarctica. Following his PhD, Holger served as a research scientist at NOAA NCU. There he measured water vapor and ozone in equatorial, mid-latitude, and polar latitudes, studying tropical cross-tropopause transport and long-term trends, as well as studying the recovery of halogen oxides in the polar vortex. From NOAA, Holger moved to a senior scientist and head role at GCOS Reference Upper Air Network in Lindenberg at the German Meteorological Service. In 2014, Holger returned to Colorado to join NCAR's Earth Observing Laboratory, where he continues to develop and deploy in situ instrumentation to measure the atmospheric state using balloon-borne and Dobson instruments and study processes controlling tropospheric and stratospheric water vapor, temperature, and ozone. Please join me in welcoming Holger for his seminar, From Glass Bulbs to Breakthroughs.
Thank you, Sarah, for that kind introduction. Welcome. It's my pleasure to tell you a little bit about a project I'm really excited about, and it's been going on for the last 20 years, which we call Ticosonde. But as I was preparing the presentation, I thought, hey, where do we actually come from and why do we do this? And so here I show a slide that some of you might be quite familiar with. That's the original figure from Brewer and Dobson's paper that shows the Brewer Dobson circulation in the stratosphere. Everybody knows Brewer Dobson circulation, and so that's the background of the entire project. And so I thought, well, how did that come about? Why did they actually come up with that idea? Well, it all started with simple measurements of water vapor over England. They had some measurements of helium flask samplings of helium, and back then the idea was that the stratosphere is probably pretty well mixed. But then they did these water vapor measurements over England and said, well, it's too dry. That air must come from the tropics. So a few measurements right there, and they deduced that figure, which is pretty spectacular. Well, next question, well, how did they even measure water vapor? Because it's all about measuring. And even there is a big story. So let me actually go back and start with how do we measure water vapor. So the first instrument that I could find to really measure water vapor is from John Frederick Daniel. He became later professor at the new formed King's College in London. He also created an electrochemical cell by his name, the Daniel cell. But one of his first things that he built was a dew point hygrometer. And it's a very simple instrument. It's just two glass bulbs. And there is ether in those two glass bulbs. You wrap a cloth around the right side and cool it on the outside with ether. As a result, you lower the vapor pressure inside that tube and force evaporation on the left side of the tube. And that evaporation on the left side of the tube cools the ether, and that goes on until you form condensation on the outside. So all you have to do is measure the temperature of this ether bulb on the left, and voila, you measure the dew point. So that is the basic principle back then. And it actually hasn't changed all that much up to today. So for the next 100 years, something like that, they would use. Here is a early dew point hygrometer that they used in food processing. You see at the very bottom, let me see, here I'll try that with a mouse. I hope you can see it. At the very bottom, again, there is a little bulb with ether, and you pump air through it, force evaporation of ether. There's a thermometer in there. There's a mercury thermometer in there, and you look at that with a telescope here on the top. You can both watch that bulb and the thermometer, and when condensation forms, you can read the temperature, and voila, you have the dew point. It's very manual work. It's a really tough one. So a little bit more development work was needed. So here's a next instrument by Charles Warren, Thornthwaite. And some of you might know him. He actually did some climatology zones. Thornthwaite climatology, I think it's maybe you know that, Sebastian. But he also built, so his climatology is very much based on evapotranspiration and the water cycle. And so, well, it was obvious he had to build an instrument for that to measure water vapor. So he built an instrument where he had a coolant here at the very bottom. He cools a mirror, and he looks at this mirror with an optical arrangement. And he can measure the temperature with a recorder, and it's just an on-off controller. If the condensate on that mirror exceeds a certain threshold, you turn the heater on or you turn it off. And that way you can control, again, the dew point. So that's the first electronic instrument that I could find. Well, next comes then, indeed, Alan Brewer. And he actually was a meteorologist. He worked at the UK Met Office at the time, and he was an instrument maker. So he was really good in building instruments. In fact, from the UK Met Office, he worked in at the Royal Air Force during World War II. He became professor at the University of Oxford, where he built the Oxford Q ozone sonde, went to Toronto, University of Toronto, and built a Brewer spectrophotometer for ozone. But one of his first instruments was a Frostpoint hygrometer for an aircraft. And very similar arrangement as the earlier one, the Thornthwaite ones. You had here a coolant. You have a mirror up here. You watch it with a small little lens. The coolant you would pump into the bottom of this mirror. It's a little thimble, and you would pump it manually with a little pump in there. So you would control the temperature that way. And you would look down and just control the temperature and, until you form dew or condensate, and you would read the temperature of that mirror. He actually had to build several versions of that one. So the first instrument flew on a, now I can't remember the instrument. It was actually, the second one was a Stratofortress. And the third one was the Mosquito. Was a higher altitude aircraft, and most importantly, a pressurized cabin. So he would have built a second version for a pressurized cabin. But yeah, so that's what he did. And it turns out those measurements were quite spectacular. Here's the very first one they did back in December of 1943. On the left, you see the frost point. On the right, you see the air temperature. And they saw near the tropopause nearly saturation. And suddenly, the frost point was just drop off very sharply. So the air was really, really dry. In 1943, well, the question is, why did they go and measure stratospheric water vapor in 1943? It was World War II. Well, that's actually the answer. It was World War II, and they realized that the bomber rates going to bomb Germany, they would be discovered by the contrails. In fact, there's some speculation that they lost over 90 planes in one particular air raid due to the contrails, so the Germans could see them early and respond earlier. So it was really important for them to figure out, like, hey, can we do something about that? Do we understand atmospheric water vapor enough? That was the motivation for these measurements. And voila, we know the rest. They figured out it was really dry. His first publication actually was on the contrails. But working with Dobson, both of them meteorologists and really ingenious, they figured out, hey, why is it so dry? And voila, the next big publication they did was their famous publication on the Brewer Dobson circulation. Well, but that was only the measurements here in the lowermost stratosphere, just as high as the aircraft could do. 37,000 feet, 40,000 feet at best, not much higher. So the next question was, well, how does it look higher up in the stratosphere? Does it hold all the way to the top? So here comes Earl Barrett. He was at the University of Chicago. University of Chicago at the time was the prominent university for meteorology in the country. Werner Suomi, Carl Gustav Rossby, Ted Fujita, they were all working at the University of Chicago, so it was very obvious. Hey, that's a problem that you can do. And Earl Barrett, he said, oh yeah, we can build an instrument. He and Lee Herndon built a Frostpoint hygrometer that they could fly on a balloon. There on the right-hand side, you see a picture of it. It's quite a big instrument, 46 pounds, quite heavy. They used quite a big balloon for that. And they flew it all the way up to 30 kilometers. Earl Barrett actually did another work with Werner Suomi, and that is he built the first sonic thermometer and laid the groundwork for sonic anemometers with that. So that also goes back to him. So here's the very first few profiles that they measured in 1949, 1950 in Minnesota and Ohio. And the mixing ratios they measured were somewhere in the tens to hundreds of parts per million. So quite a bit higher than what the English showed with their aircraft flights. In fact, the UK Met Office flights, they continued all the way into the mid-50s. They flew out of England, of course, and North Africa. They did a few measurements. And typically, they were really, really dry. These measurements were quite wet. And so there was a big puzzle. It's like, what's really going on there? So the next step then was John Massenbrook. He worked with New York University, who had started building another Frostpoint hygrometer in the 50s, and he took that over, continued working with them at the Naval Research Labs in Washington, and he built an instrument that was quite a bit smaller, and he recognized some of the limitations that the early balloon measurements by the University of Chicago had. Most importantly, he recognized that contamination, self-contamination, was the big problem, that you carry water vapor in your instrument on the balloon. So he used a very large separation between the balloon and the instrument, an unwinder of like 300 meters. He used descending sounding, so either put two balloons up where one would burst and the other one come down slowly, or a big parachute. He also recognized that with a frost layer you have to be careful, so he already implemented some mirror cleaning cycles. So this mirror, that you actually erase it during the flight and reform the frost layer. And of course, this instrument was a factor of 5 lighter than the previous one. John Massenbrook was also very active in where he was measuring. So the very first flight was somewhere near Denver, together with the National Weather Service. And I could not find exactly where it was, whether it's here in Boulder or somewhere else. Neither NCAR nor the NOAA labs weren't there yet, but the early seeds of them were already here. So it's very likely that was done somewhere here in Boulder. And then in 1960, started a few measurements in Washington, D.C. at the Naval Research Labs. In 1961, there was a very big field campaign, the American Indian Balloon Program, and he went as part of that one to do the water vapor measurements. That was a big balloon program to measure chemistry in the troposphere and the stratosphere, aerosols, and it was very, very massive. Christian Junger, for example, was there for the aerosol measurements. And he did 3 soundings. Now, they were not terribly successful, and I couldn't even find the data for it. But that was the very first ones internationally. Then in 1963, he went to the Kwajalein Atoll, Western Pacific. They already knew this was very cold. The tropopause was very cold. So he went there to do a few soundings. And then he did a 2-year program, 1964, 1965, out of Trinidad in the West Indies. And I'll show those data actually in just a bit. He interrupted that program to do measurements in Thule and started then a regular program in Washington. So in 1965, he did measurements in Thule, Washington, and Trinidad to look, is there a latitudinal gradient in his measurements? And yeah, from 1964 through 1980, he continued his measurement program in Washington, D.C. When he retired, he got in contact with Sam Altmans at NOAA, who was my boss. I joined him in 1991. And the program was moved from Washington, D.C. to Boulder. So 1980 is actually the beginning of the long-term monitoring program in Boulder. And I show that as one important little difference, which is why we can't string those 2 data series together. We'll get to that in a second. But yeah, so here's a picture of the actual balloon launch in Kwajalein. It was quite a large effort. There was a 7,000-gram balloon. And took 4 people to launch. Now you can do it with 1 or 2, but still this was very ingenious. And you see here the instrument on the very left. It's not terribly large, actually. Here are the 2 profiles, 2 out of those 5 profiles. In fact, I think those are the only 2 good profiles. A little bit smooth, a little bit of noise in there. I smoothed that out. But quite a bit difference between the 2. But the key statement is it's still the stratosphere is really, really dry. And that was basically one of the important ingredients to solving that mystery. Is it stratosphere dry or is it wet? But yeah, the absolute accuracy is a little bit of a challenge, and it made it hard to interpret it. And that goes back to the instrument itself. So here is a cross-section of the mirror. The instrument that John Massenbrook built had a heater on the edge of the mirror and the coolant in the center of the mirror. And it was on purpose that there was a strong temperature gradient here. This is a temperature gradient along the radius of the mirror, with the idea that prior to launch, you adjust the condensate layer so the edge would sit exactly across the thermistor. So that exactly where the thermistor is, that's the dew point or frost point. Except what happens if that frost layer doesn't stay stable? If it moves, then the gradient moves. And that's the limitation of those measurements. That's why they change a lot from sounding to sounding. Here's the data record from Trinidad. All 20-some profiles and 27 or 23, however many it is. And you see all of them, well, they scatter a fair bit. But the key statement compared to the University of Chicago measurements, the atmosphere is the stratosphere is really dry. So that solved that issue, yeah, was it the British measurements, the dry stratosphere? Was it the American Chicago measurements, the stratosphere wet? That ultimately solved it. No, it's really dry. Now, this is now order of magnitude. Now we're dealing with like 5 or 10% issues. But that was a very, very important answer. One last technical development here coming also from Boulder, in this case actually not Frostpoint, but again it's an important technological breakthrough. Dieter Kley at the time at NOAA, he built a Lyman alpha hygrometer. And that flew first in Brazil in 1978 and showed a profile that was very, very similar to what Mastenbrook was showing. And most importantly, he showed that there was a minimum of water vapor above the tropopause right here, and he called it a hygropause. That's where the term hygropause comes from. And interestingly enough, they didn't quite add one and one together, even so he already made that statement where the dry air came from and said, oh, maybe that comes from a little bit earlier when the stratosphere, so when the tropopause was colder. So maybe that's older air, like a few months old. But that was all they said. Well, I stay with the balloon-borne theme in my talk. I do want to acknowledge there was a lot of aircraft measurements. Yeah, they started all in the 80s and then the satellite measurements, 80s and 90s, that added a lot to the water vapor theme and water vapor research in the stratosphere. But I stick to the Frostpoint measurements because I want to get to my Ticosonde program. So in 1993, that was actually my very first field campaign, CPEX, C-E-P-E-X, was the balloon-borne measurements along the equator, actually 2 degrees south, between Honiara and Christmas Island. And I'll show you those data in a second. There were a small program, observation in the middle stratosphere, OMS in Brazil, and the sour measurements in Galapagos, soundings of ozone and water vapor measurements. They ran from 1998 till 2007. I ran that one. And then in the Western Pacific from 99 to 2015, my Japanese colleagues. Yeah, and then in 2005, Ticosonde started and is still going today. So here's the key measurements from CPEX. And we found basically 3 different regions, what was really interesting at the time. On the left, so here's the track here, the ship track, and we actually released balloons. And here the first third of that, so the first 4 soundings, I think, are these here on the left side, where we always saw a saturated tropopause at really cold temperatures and saturated tropopause. Then in the middle section, before getting to Christmas Island, the tropopause was no longer saturated, it was quite a bit warmer. And then quite a bit warmer yet on Christmas Island, which was on 2 degrees north. So we did see a longitudinal gradient of temperature across the Pacific, but not in water vapor. Well. And then the sour measurements, they focused on a few stations. So actually I didn't put it in here. Costa Rica is right here. Cotabang in Indonesia, in Western Indonesia, Biak, Eastern Indonesia, Tarawa in the Central Pacific in Hanoi, and the color contours, they give you a temperature on the 370 K isentrope, so basically the tropopause. So Tarawa was in the coldest part of that region. Costa Rica here on the very right is sort of in the middle. Biak also very cold. Cotabang, somewhere slightly warmer in Hanoi there. And these are the measurements that we have. Again, they all look fairly very similar, except here in the tropopause region, that's where you have the biggest differences. Those are the differences due to the temperature. And I even have here one of the Ticosonde profiles on there. It's a red one. And again, it's a little bit wetter here, and the tropopause region is a little bit wetter there. So that's where you have the biggest differences. But in the stratosphere, in the deep stratosphere, actually it doesn't matter where you measure. And the right-hand side, relative humidity over ice. So you see where you might have saturation, where this drying that Brewer and Dobson were speculating, where this actually happens. We see it right there when the air gets saturated relative to ice. So let me get to the Ticosonde water vapor and ozone soundings that started in 2005. So it's a balloon-borne sounding program. We fly monthly cryogenic frostpoint hygrometers, every other week an ozone sonde, at least that's the program right now. The radio sonde we use is an Intermet IMET 4, but we actually did test a number of other ozone radio sondes as well. We had the Weissler RS92, the Weissler RS41, and IMET 54. We even had a flash hygrometer on there. I'll get to that later in my talk. And if anybody is interested about, on this data, they are all freely available at the NDOC archive for water vapor and the Shadows archive for ozone. And Jackie sits there. She was the Shadows data manager. She knows these data really well. Yeah, so Ticosonde, it's actually a very interesting cooperation between a number of institutions. It's NASA-led, that's where all the funding comes from. Universidad de Costa Rica right now is our main partner, where all the work is actually happening. NCAR, it's myself, NOAA, Universidad Nacional, we started that cooperation with them. We also work with the Instituto Meteorológico Nacional. UMBC was part of it, and even CU. I absolutely want to acknowledge my main partners, co-conspirators, Ryan Stauffer, he's the main PI at NASA right now. Before that, it was Rennie Selkirk until he stepped away from that position. And I actually was the very first PI when that started in 2005. And Holger Andres Diaz, he is our partner there at the moment. And I absolutely do appreciate the work that all of them put in there. What was also really interesting, at the very beginning, our first campaign, Tropical Cloud System Processes, TCSP, was a very intensive balloon campaign. There we flew, I think, 25 frostpoint hygrometers in as many days. So one a day, more or less. And that took a lot of work, and I got a lot of help. So there was a lot of students involved, which was a great learning experience. On the left-hand side, students from the chemistry laboratory at the Universidad Nacional, who helped me a lot. At the right side, students from the Universidad of Costa Rica, who were more working with the radio sondes, but we're all working in this very first few deployments together. And what's really interesting, one of the guys on the right, he's now the dean of the physics department. This guy here on the very left, he's now the head of the atmospheric chemistry lab at UNA. Second to the left on the right picture, he's now running the radio sonde operations at the Meteorological Institute in Costa Rica. So we actually had quite some influence on the students. It was a lot of fun to work with all of them. And that's our current launch team as of a couple of years ago and still today. That's Alfredo Alan, Fernando Rojas, Ernesto Corrales, and Jorge Andres Diaz on the right side. And that's our 800th launch sometime earlier this year. Again, a CFH, ECC ozone sonde, and a radio sonde. So that's what we've done many, 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 many times over 20 years. So there's a lot of data with that, and so let's look a little bit at some of those data. So first of all, let's look at the climatology, so I'll give you a little bit of perspective. In terms of temperature, Costa Rica is really, really boring. Unlike Boulder, we have a big seasonal cycle. They don't have a seasonal cycle. Year-round, it's more or less the same temperature, except, of course, for the tropopause. The tropopause is really cold, and they're November through April, May, and then in our summer, June, July, August, their tropopause is really warm. That's where they have their big seasonal cycle. In humidity, it's even stronger, of course. They have a rainy season and a dry season. And you see that really nicely in the climatology of relative humidity. And in case I didn't point it out, every little arrow at the bottom indicates one balloon launch. Now, so you roughly have an idea of coverage of balloon launches. They're not equally spaced in that particular. And I threw all 20 years together for these plots. But yeah, so you see here, this is relative humidity over ice above the freezing point. So you can translate it to ice saturation at the tropopause. And if I plot it like this, there isn't much ice saturation at the tropopause. But that actually is an artifact of my smoothing here, because I average by altitude. What I should be doing, I should adjust all tropopauses first and then average, and that's what I did here. So here I adjusted the altitudes of all profile, lined them all up at the tropopause rather than the surface. And voila, now you see that red color very close to ice saturation, almost throughout the year. So the original idea from Brewer and Dobson, that this dry air that they saw over England comes from the tropics and was dried out of the tropics, here we see this drying out. And what's really interesting, there was always this question, well, how exactly is this drying, how does it work? We don't observe any particles, so I can't tell you any of the microphysics. It would be really cool if we had any, but I can tell you about the relative humidity. And here's the relative humidity distribution, and that is really fascinating. So if I average the relative humidity of all of those profiles, it's about 250 Frostpoint profiles, and the rest is all ozone. Relative humidity at the tropopause, on average, is 100% saturation of ice. In fact, the mean is 100.3. Which is remarkable because there's no reason to say it must be 100. Only, of course, when it's ice saturated or when it's exactly at saturation, but why does it average out? But that's how it does. And there is an important implication of that, which is if you model that, if you take any model and want to calculate how much water vapor does go into the stratosphere, and you calculate the saturation mixing ratio and say that's how much water goes in there, that's a good assumption. There is no microphysics. It's like, oh, the particles have to be supersaturated. Or we evaporate a lot of particles in the stratosphere. Maybe, but on average, 100% at the tropical tropopause, use that as your saturation mixing ratio, enters the stratosphere. That is a good assumption. But of course, a little more complicated. Here I did do the same thing now, monthly resolved. So this is all the points I have for both the WMO-defined tropopause, so 2 kelvins per kilometer over 2 kilometers, and the cold point. And it turns out over Costa Rica, the difference is not large, but it's there, and it's significant. And so the one lesson, so the blue dots and the blue line, it's a little bit less than the cold point. That means the cold point, where you should really have your drying out, it's a couple percent less than the 100% I showed you at the WMO-defined tropopause. So there's a few little details to that story that are still hidden. And another important thing, the one thing that sticks out, that in March and May, we seem to have a minimum and a maximum in this particular distribution. However, our sampling isn't that great. In particular, in those 2 months here, we don't have all that many soundings, because when I say 250, it sounds like great. Divided by 12, so it's maybe 20 per month. But then consider also we had these really intensive campaigns right here as TCSP and TC4. We had here a very intensive campaign, CRAVE, where we launched a lot more in one particular month. So we have a sampling bias here, or sampling limitation. So I wouldn't subscribe that there is a seasonal cycle in this RH. I would still maintain, on average, 100% is probably a good one. Well, let's look at the water vapor mixing ratio. Now we know it was saturated throughout the year, so this dehydration process can happen throughout the year. But because the tropopause is warmer during the summer, that means you get more water vapor in it. And that's what this plot shows. So here we have a nice seasonal cycle of the water vapor right at the tropical tropopause. And that goes into the stratosphere. So, and let's look at the tape recorder, and I don't see any very young people. The young people on the audience, you might go to a museum or ask your parents whether they have a tape recorder, and I can explain you why that's called a tape recorder. But here's all our 20-year record of water vapor measurements at Costa Rica, now color-coded over the entire, and you see color-coded over the entire season. And you see here a sequence of darker blue and greenish colors, so drier, wetter, and they seem to be moving upwards. So this moving upward, I show you in the next slide, that's what we call the tape recorder. And in fact, right here just take 2 years out of those 20 years, just 2 years so you actually see it. And so here's our January 14. It's really cold, really dry, and this dry air rises. In the summer, it's wet, and that wet air rises. Next year, same thing, and that repeats over and over again. So that's what we call the tape recorder, the seasonal variation of water vapor entering the stratosphere. And you see this only in the tropics. You don't see this outside of the tropics. Now, one really cool thing, that is the data from Trinidad, 1964, 1965. And they could have seen the tape recorder. The data quality wasn't quite as great. But you also have here this wet going up here, you have the dry going up there, and in fact the arrows are the ones from the previous slide. So in 1964-65, we already saw the tape recorder. If you massage the data properly, smooth them properly, how to get this out. Of course, at the time, they were just wondering how much water vapor is there in total. But already they could see the tape recorder. Well, another cool thing we detected was the water vapor injected by Hunga Tonga Hunga Ha'apai in 2022. So here again, our time series now from 2020 to 2026. The red line, dashed line, that's the day of the eruption of Hunga Tonga Hunga Ha'apai on 15th of January. And we saw the first little blip of it 4 weeks later. And that is actually quite remarkable because the volcano was roughly at 20 degrees south. Costa Rica is 10 degrees north. So within 44 weeks, we had this cross-equatorial transport. On the 24th of March, sounding even stronger. Then we had a couple of failures where the balloon or the instrument didn't make it quite as high. In the fall, we see a few more. And interesting enough, then the signal pretty much disappears. So the Hunga Tonga Hunga Ha'apai signal in Costa Rica is not very strong. It's very short-lived. And that's simply because we're in that ascending branch of the Brewer Dobson circulation. We can see all the water vapor coming up from the troposphere, which flushes out the water vapor from the volcano. Here are the individual profiles. And I actually put the MLS profiles on them just to show what the troubles that MLS had in the first weeks. Here, for example, especially on 16th February, the layer was still very sharp and just MLS can't resolve this sharp layer. It smooths this out. 4 weeks later, so 8 weeks after the eruption, that's what we see in Costa Rica here, 3 very pronounced spikes. MLS smooths that out a bit. And as the plume disperses, MLS gets a much better representation of the injected material later on. But we don't see much of that anymore in Costa Rica.
What's the MLS?
The microwave limb sounder on the Aura satellite. I apologize for the non-stratospheric folks. So, in fact, I have a slide I'll get to that in just a couple slides. So, this is a Hunga Tonga Hunga Ha'apai, and here just the time series. Because 20 years, we have a lot of trend data. Here I show them, and basically there isn't much happening. Costa Rica is fortunately very benign. There's not a lot of action. Here you see at the very highest level, this one goes off the chart. And I actually plot just the anomalies to make it better visible. Here it's just one sounding that gives us this really big spike. On this 24 to 26 kilometer where we have better coverage, we see quite a number of soundings, and then it comes back to background. And here, the 22 to 24 kilometer layer, hardly anything there of the volcano. So we see it only in the uppermost layer where the Frostpoint instruments still give good measurements. And for the rest, over the 20 years, there's fairly little variation or long-term trend over that one. So instrument validation, yep, there's the answer. There's the slides to MLS. So the program was funded initially very much to validate MLS. MLS is the prime satellite for stratospheric composition, and water vapor is one of the important trace gases for that. And so all the Frostpoint instruments were used to validate a MLS satellite. And so here's a very early paper a couple years afterwards where we showed, yep, the MLS data look actually pretty good throughout most of the stratosphere, and there's some biases in the troposphere, with the additional caveat that the variability in the troposphere just explodes. And so it's really hard to do a solid comparison with balloon-borne soundings. Then about 10 years ago, Dale Hurst, who took over from me at NOAA, he figured out that MLS started drifting. He saw that in comparison of Frostpoint and MLS data in Lindenberg and in Boulder. And so roughly from 2011 on, MLS seemed to drift downward. We also saw that here in Costa Rica and in Hilo, Hawaii, and in Lauder in the southern hemisphere. And the MLS folks certainly realized that as well and took that to heart and figured out what's going on with their instrument and did new processing that took care of this drift. And that's version 5 that's out now. And so that's monitoring is still going on. So here's the state of the climate report graph, for example, that Sean Davis puts together. So Boulder here, the long-term series at Boulder, at Hilo, San Jose in Costa Rica, and Lauder in New Zealand. And yeah, we're doing really well, MLS doing really well, and so that is a really, really great data set. But as I said earlier on, we also used that for a lot more instrument validation. And one of the early results was the comparison between the Frostpoint instruments and the Weissler RS-92 radiosonde. That was operationally flown in about half of all stations globally. And so in our Costa Rica soundings, we figured out, hey, that radiosonde has a huge dry bias the higher you go. Up to 50% at like 15 kilometers, very, very significant. And that had important implications on numerical weather forecasting. So I was working at the German Met Service at the time, and so they actually implemented a correction for the Weissler radiosondes and figured out that it improves their forecast for precipitation with that correction for the Weissler radiosondes, just because they had such a big impact. In our work with the IMN, we then also, once the RS-41 became operationally 10 years ago, we did a similar comparison, just not as extensive, but still significant, and figured out that the Weissler RS-41, the current radiosonde model, gives actually very good humidity measurements all the way up to the tropopause, tropical tropopause, I should say. And then once you go into the stratosphere, then it really runs off. But there is very good up to the tropopause, and there is significant sensitivity in the lowermost stratosphere. And so we're using these results now to expand our measurement capabilities with the radiosondes into the stratosphere. We also worked with Intermet South Africa. They have a radiosonde model called IMET 54. And they were quite generous and donated a whole bunch of them, and we added them to our soundings there. And could see, yep, they have a little bit of bias, and then their variability really grows as you go into the upper troposphere and lower stratosphere. So that is not as good as a radiosonde for humidity measurements. But yeah, here's a nice example that if you talk about radiosonde humidities, you really should know which radiosonde you're talking about, because they all behave very, very differently. Well, volcanic events, I already mentioned one. Here's a profile from Hunga Tonga Ha'apai. And that is actually a really remarkable one, and that's my last little thing I'm going to talk about. That particular profile also measured ozone, and we saw a big notch here in the ozone profile. And that comes from a different volcano. That's from Turrialba volcano. So that is, to my knowledge, the only sounding profile that measured 2 volcanoes in one profile. So we get 2 for 1. So we were really thrilled with this one. So we measure no ozone in this layer, but that doesn't mean there is no ozone in that air mass. I'll get to that in the next slide. Here's Turrialba volcano. Here's San Jose. Here's this balloon. That's where we actually launched the balloons. So the volcano is just 30 kilometers to the east, just straight downwind, and we very often see air coming from that volcano. And here's another example. And in this case, actually, we have 2 ozone sondes on the balloon. The left hand is the regular ozone sonde, and it shows, hey, there's a lot of ozone missing. The right ozone sonde has a filter for SO2 on it. So it filters out SO2 going into the sonde. And that shows there is actually air and ozone in the air, and there's also SO2 in the air. And the SO2 messes with the chemistry in the ECC ozone sonde. So it just makes it look like there is no ozone, where in fact there is normal ozone, but there's SO2 in it. So our ozone sonde becomes an SO2 detector when you see these notches. And we see quite a lot of them. In fact, we see so many that we can do a little bit of climatology on that one. And so the red dots is the integrated column SO2 from these notches, from all of those ozone sondes. And the blue dots, that's from the OMI instrument on the Aura satellite looking down, measuring the SO2 column. Now, OMI gets a lot more because they get almost daily overpasses, so they see a lot more. We only get soundings about a week or so, or every other week. But most importantly, we can see when the volcano is active and when it's not active. And that just by coincidence. And so here in 2010, the volcano was very active, and here, in fact, we had 15, 16 Dobson units of SO2. Our column, we missed like 6 or 7 kilometers of ozone because there was so much SO2 in the air. And then since 2020, the volcano has calmed down a fair bit, and we see a lot less of those, but still occasionally. In the last year, we have seen very little. And I'm waiting to see when we see the next little notch, because OMI seems to indicate that the volcano might be picking up a little bit. But yeah, so that was just a little side effect. I could have talked a lot more about ozone, but I only have 45 minutes. So I thought I'd show this one because that was a nice side effect. It also initiated that Gary Morris, who actually came up with this technology to put an SO2 filter on it. University of Houston, they're working more on this, and actually they put an ozone filter on it and biases on, so they work more to do a better quantitative measurement on the SO2 with the ECC. So again, here's some technological development that was initiated by that project. So it's just a really nice side thing. So with this, I end here. I give my summary there. So the Ticosonde program is really the only long-term program for UTLS water vapor in the tropics. There's several ozone sound stations. Of course, Costa Rica is one of them. But it is indeed the only station for stratospheric water vapor. And with that, we can monitor the entry region for water vapor into the stratosphere. What exactly Brewer and Dobson had postulated 80 years ago. Yeah, the program builds really on 80 years of work. So there's a lot of work, and I hope we can continue doing this. The cooperation with IMN, with UCR, with UNA has been really, really fruitful. And we've had a lot of flexibility to add extra sensors, do new stuff, and so really expand the program, which made it really exciting. And yeah, lastly, we expected something we didn't think of we would expect when we set out with that. And so with that, I thank you for your attention.
Thanks, Holger, for that very historical and informative talk. While those in the room are thinking of their questions, we have a question from Andy that was about some of your earlier material. He says, why is wet bulb rather than ice bulb temperature used, even though the latter is appropriate under some conditions such as ice crystal sublimation?
Why is wet bulb rather than ice bulb temperature used? So I was always shown frost point temperature or relative humidity over ice. That issue of wet bulb or ice bulb, I think that plays more role in warmer regions when you actually have a psychrometer or can do this truly bulb measurement that the very first instrument had. With the mirror instruments is really, do you have ice on the mirror, do you have frost on the mirror? But in the upper troposphere, it's always ice, so there you have no issues with that. It is a little issue in the middle troposphere around the freezing layer. I didn't go into that detail. With the frost point instruments, you have to be very careful at mirror temperatures below 0 degrees C. Between 0 degrees C mirror temperature and, let's say, minus 25, minus 30, you may have liquid on the mirror or you may have ice on the mirror. And if you don't know what's on the mirror, then you use the wrong vapor pressure equation and get in trouble, which might be behind that question, Andy. But with the frost point, with the CFH, we actually control this. We force the condensate to freeze, so we know for sure when we have ice and when we have liquid. So it's not an issue. And I hope that answers that one.
Interesting. Sebastian?
Thanks. A really nice talk, Holger, with the historic context and everything. It's great. What do you see in the future? Do you guys have funding to continue these measurements, or what are the future plans?
We actually just got our grant renewed, so we're starting right now our new grant funding cycle, so we have another 3 or 4 years more funding. And I hope it will continue after that because it's such a unique site.
That was a very interesting discussion of the history, but you didn't say too much about what the technology is now, how it differs from what was used in the past. So could you enlighten us a little bit more on?
I didn't say very much about it because not much has changed really. The basic measurement principle is exactly the same. You cool the mirror till you see frost. Actually, you maintain a stable frost layer. And the stability of that frost layer, there's a little caveat to that. But once you maintain a stable frost layer, you assume that the temperature of that frost layer is equal to the frost point temperature. That was early then, that's still today. Now the only difference is now it's microcontroller and LEDs and smaller electronics, but the physics is exactly the same.
So how is the cooling done nowadays?
In fact, it is exactly done the same as Warren did. Yeah, they used R23 back then for the cooling of the mirror and as a hypsometer for pressure measurement. We now use GPS or solid-state instruments for pressure measurement, but the cooling was done exactly the same back then. Right now, in fact, we're switching away from the R23 and we're going to liquid nitrogen. And that's because it's banned by the Kyoto Protocol, the Kigali Amendment. So we can't use that anymore.
So what's R23?
It's the coolant. So it's one of the CFCs. Okay. Actually, not a CFC, it's a HFC or whatever it's called, not chlorine containing, but it's a strong greenhouse gas. And that's banned in the Paris Agreement.
So by evaporation?
Yep.
Okay. That's.
Any other questions?
Thanks, Holger. Very interesting. You highlighted some injections of water vapor into the stratosphere from, say, volcanoes and other events. I'm just curious if you've seen anything related to tropical convection itself. For example, Niño versus La Niña. I know Costa Rica doesn't get hit by hurricanes often, but when you have very powerful hurricanes in the Gulf of Mexico or Caribbean.
That is a really good question. And there is actually one profile I could show. We might need to discuss it. In 2005, when we started, this was also a very active hurricane season. Mm-hmm. And there were two really strong hurricanes, Hurricane Emily and Hurricane Dennis. And we launched, that was right during TCSP, and we launched a Frostpoint and Ozone instrument within a couple of days. Now, those two hurricanes did not impact Costa Rica at all. Yeah, they slammed into the Texas coast, churned up the Caribbean and the Gulf of Mexico. But the dynamical response was felt all across Central America. And we saw the strangest water vapor ozone correlation in one of those two profiles. We have not seen it again. Okay. And so there was something going on with the transport around the hurricane. But other than that, we haven't seen anything there. The other part, well, I'll talk to you afterwards on the hurricane stuff.
Thank you, very interesting.
Yep.
Ready?
Yep. Great. Any other questions in the room? Okay, then I have one while they're thinking. So you mentioned that you don't have any particle measurements on these, but you did mention that there were intensive observation periods around TC4 and Crave. Have you done anything to look at cirrus cloud occurrence during those IOPs?
No, I personally have not looked at it, but there's other people who have looked at it. At that time, especially Crave was one of those campaigns where there was still a lot of discussion about the accuracy of the water vapor measurements. That issue has disappeared since then over the last 20 years, but all the way up to Crave, there were different instruments on the ER2 from Harvard and from NOAA, and I don't know who else was on there, and they showed significant differences. And so there was a lot of discussion who is actually right. Harvard measurements, and in Crave in particular, being a factor of 2 larger than Frostpoint instruments. There were probably some particle measurements along with it. I'm not quite sure how much they actually crossed the tropopause in that. So yeah, I can't really answer that question.
That's fair. Any other questions in the room?
Hey, thanks for the nice talk. So I was just wondering, MLS is ending soon, I guess. MLS is observations from satellite. MLS is ending at some point soon.
Yep.
Do you know, is there something on the pipeline after?
It'll be
After that?
very thin after MLS. So Aura MLS, it was launched in 2004. It's on its 21st year. It's going to be turned off, I believe, in January of next year, if I'm not mistaken. So it was supposed to have been turned off 2 years ago, is that right? And there was a huge outcry from the community, and luckily somebody at NASA had an insight. I was like, that's not a good idea, especially after the volcanic eruption. But it must be deorbited in January of next year. So as far as I understand, there's no possibility to extend it. There are still a few other satellites in orbit, most importantly SAGE 3 on the space station. And I'm not quite sure how much longer that's going to be up there. It's also just a couple more years, maybe. I don't know exactly. And then there's ACE FTS, which is even up in space longer than MLS. But they don't have to come down. They can no longer control their orbit, but they can still measure just fine, and so they will keep going as long as the spacecraft holds together, which hopefully is for a long time. But that instrument is focusing more on polar latitudes, high latitudes, and does very little coverage in the tropics. And after that, it gets very thin very quickly. So there's something on the distant horizon, but there will be a very significant gap in stratospheric water vapor monitoring. And so for that reason, it's actually important that we maintain all of those stratospheric sounding sites that we have. I showed 4 of them, and there might be 2 or 3 more that go routinely. It's not many, and we probably will need all of them once MLS is done.
All right. Well, I don't see any more questions online. So if there's nothing else pressing in the room, we'll leave a couple minutes for those side conversations. Let's thank Holger one more time.